Hi guys, in this video I will show you how our interface for code generation can be used for turning our calculator into a simple compiler. The first and actually major change will be how we handle expressions. So far we have this method for evaluating an expression. In the calculator we used it to immediately compute the value of an expression. This function will go away. We will replace it with a function that produces assembly code for loading the value of an expression into a register. And on the next slides, I explain you in more detail what it actually means to load the value of an expression into a register. Let's begin with the simplest case, that we have a primary expression. Then in our case, it means that it's either an unsigned integer literal or a variable. If it's an unsigned integer literal, then we simply have to generate assembly code for loading an unsigned integer literal into a register, and for that we simply can use one of these functions from our code generation interface. If it's a variable, then in our case it's always a global variable. That means we first have to load the address of this variable, that means the label of this variable, into a register, and then we have to fetch from this address this 8 bytes into this register. And that's it. In our case, the unary expression nodes actually can be seen as a special case of binary expression nodes, where one expression node is simply having the value 0. So let's simply skip this case, and you will see in the demo how I will handle this case by mapping it to the case of a binary expression node. If this binary expression node is representing an operation like adding two expressions, then we simply can make a recursive function call for loading, for example, the left subtree into a register. Then we will acquire a temporary register and will load into this temporary register the value of the right subtree. And then we can simply apply the operation. For example, here adding the values of these two subtrees. You will see that it is kind of more convenient to actually swap, in our case here, this operands, because we also have to deal with subtraction and division, and how we define the interface for assembly generation. It will be actually better if we have it this way. Then you can reuse this pattern for all these other binary operations, except for assignments, which is the special case that I want to handle next. If we have an assignment, then we have to load the address of the left-hand side. In our case, that's always the address of a variable into a register, and also the value of the right-hand side. And then we simply store the value of the right-hand side at the address of the left-hand side. You will see in the demo that if we change here the order a bit, so that we first load the value of the right-hand side and then the address of the left-hand side, we in general can save a register. Now, before I continue, let me already start in the demo with the implementation of this new interface for expressions. And in this first approach, I just implement a few operations or support a few operations. And then I will turn this calculator into a compiler. And with that, I have the possibility to test more, and then I will also implement more. First of all, I want to set up some test for the new expression interface. And for that, I simply modify the current existing test for expressions. I want to have a few expressions, print the expression trees, and then later generate code for it. So let me first remove most of this here. And then I change this binary expression into an assignment of a literal into a variable. And then I first want to make sure that we have a test case that compiles and can be executed. Okay. So now let's check that there are no typos or missing parentheses. Okay, and so the current output, is now this expression tree. And now I want to have a second expression tree for another assignment where I have here another binary expression node. So let's change it first like that. Okay, this of course also should be assigned to. Okay, now we have two expression statements, and of course this later can be changed to whatever operations we want to test. Okay, now let me use here in this terminal for the interface first. Here we have to get rid of a few things. And here I have to add the header for this code generation. Then I want to have the typical scenario that the code generation interface gets used to produce some code. So that means we will first acquire a register, and then every time we have an expression statement, the expression of it will be loaded into a register. And then we release it. So this later will be done in the parser. And here I want to load the second expression into this register. And now here we also need this interface for code generation, and we have to get rid of this expression kind power, and we replace this function with load expression. Okay, and then we already can test whether we have typos by trying to generate here an object file. So this works, and that means now we can begin with the implementation of this function. So here I begin with a stop, and then I have to get rid of this code for evaluating an expression. Okay, now let's see if the changes now can be used for generating an executable. Okay, more things need to be removed, of course, also this expression kind here. So this is always the annoying first step if you have some existing code and want to change it into something new. Okay, then in the parser we are also still using this eval expression function, and because all source files will be translated into object code, we also already have to make a modification here. Let's simply remove it for now. And another one. Of course, we also have to actually change the grammar already for the calculator. I will come back to the new grammar later. Let me already show you how it looks like. We simply will call here pass unary expression, because we no longer have this power expressions in the calculator. Wouldn't make sense for unsigned integers. Okay, and now we have some setting where we actually can test the new interface. So after this bootstrapping part, we now can begin. So here we first have to check whether we actually do have a pointer to an expression, the usual things. Then we also should check whether we have a expression kind that is actually valid. So the usual pattern, it should be in this range. Okay, and now we handle the different cases, whether it's a binary expression, unary expression, or primary expression. And I first want to make sure that this structure for handling all these cases is set up correctly. The case for primary expression actually consists of two cases that I simply will handle with extra else if branches. And then the idea will be if the expression could be handled properly, then this function will return before we reach this statement here, which will issue an error message and then we'll call finalize exit. And then maybe we also print out what expression kind wasn't handled above. Okay, and this already would be something that can be compiled into a executable, hopefully. And of course, this always will produce now an error message for whatever expressions you want to load into a register. And then we can actually begin with some first implementation. The simplest is, of course, loading the literal into a register. So just lots of typing. And whenever we handle the case, we return. So this is the general idea of this implementation. Okay, no typos. Then the next case that we have an identifier, then we have to load first the address of this identifier. That's simply its label into the destination register first. And then fetch from there the value. And in our case, all integers are 8-byte integers unsigned. Okay, and then this case is also handled. Again, let's check for typos. And then we can continue here with the binary expressions. And here I want to have a variable for the left and right subtree to save a bit of typing at least. Okay. And then I will handle all cases with a switch statement. So And initially it will be just handling actually adding expressions and assigning expressions. And this is basically what you saw on the slides. And here I will first use this order that I showed first, that I'm loading the right expression into a temporary, and then I use our code generation interface in a way that I first have this value of the left tree in the destination register, then I add it to the temporary register. And later you will see that actually swapping this operands will make sense. Okay, then we also have handled this case, so let's return. And then we also have this assignment, and also this will be done like shown on the slides. Here we actually first have to check whether it's an L value, what we have on the left hand side. Then I can copy paste this long line of code. And here I also will first load the address of the left hand side into a register. So this non-optimal variant for handling this case. This of course has to be left. And this address. Okay, and then I load the value of the right hand side into the destination register. This also will be the value of this expression node. And then I store the value of the right hand side at this address of the left hand side. And just to get no warning, we also have a default case. Okay. So now this already should produce some code for these test cases. Now let's see what this code is doing. So here we first load the address of the variable into register 7, the value of the right hand side into register 6, and then we store the value. And here in this second assignment, I actually see that I wanted to have a different operation on the right hand side. I wanted to add here the two child nodes. Okay, let's recompile and rerun this test again, and then you will see that in general we waste a register in assignments. Okay, so this is now the assignment, and here we first load again the address of the variable on the left hand side into register 7, and after that we load again the address into register 6. Then we fetch the value at the literal, and then we store the result. And now if I reorder here things, so that I first load the value of the right hand side into register, and then I acquire a new register, then I don't need this register 8 anymore. I do not get rid of loading this address of the variable twice, but I need one register fewer. Okay, so that's it for the first test. Of course, now I want to test a bit more. I also want to test the other operations, and I also want to implement them. But for that, I need a better test case. And the next test actually will be the compiler. And I simply rename this test program for the calculator into a test program for the compiler. Let me prepare this already. So I simply rename this. And then actually before I continue, I will tell you what kind of features I would like to have in the compiler. You already saw that I changed the grammar in order to translate the parser into an object file. We no longer have these power expressions. There will be, however, another change. We also want to support the computation of the remainder in a division. Then for the parser, I also want to have the possible feature that the parser generates not just assembly code that can be written to a file, but also optionally some debugging information, some LaTeX code for representing the expressions and how these expressions will be mapped to assembly code. And then, of course, we want to have a compiler that generates assembly code that can be translated into an executable. And I will show you this next, step by step, how we in the end have some compiler actually for this simple programming language so far. Okay, let's begin with the handling of this file I/O. There will be a second optional program argument. Out will be used for the assembly output and logout for this LaTeX code. And then I have to change here the code for handling the arguments. If we have two arguments, then I have to open this log file. So this will be changed to opening the log file with this file pointer logout, and the file name is the program parameter with index 2, also here. And then here the parser will generate the assembler code, write it into a file for the assembler output. And I will change this interface for the parser so that we can specify two file pointers. So this header for the LaTeX code will go also into this file. And then I also have to close both file pointers if a file was opened. Okay, annoying stuff, but that's necessary. Then I have to change the interface for the parser so that we also can specify this parser output. And now let's see whether we have some typos. Okay, no, that's okay. And then I can continue with modifying the implementation of the parser so that we support also this assembler output. So that means I need another file pointer here, also a static variable. Okay, so now this sets the out file pointer. And this also sets the output for the code generator. Okay, and then I have to change things here. So what was out before is not now log out. Okay, so that's it. And now when we have passed the expression statement, we want to load the expression into a destination register, which I get from here. And afterwards, I have to release this register, of course, again. And then in between, we have to generate code for that. So now this code will automatically go into this file for the assembler output. But in between here, I also want to have this assembly code in this log file so that I can see it next to this graphs for the expressions. That means here I have to do some kind of a hack. I, for a short while, set the output for the generator also to log out, and then I set it back. Okay, now let's see how this works out. Okay. So this is the assembler output on standard out, also here. Then let's use one file for the assembler output. Okay, that means afterwards we should see this code in foo.s. And now let's also generate some log file, some LaTeX file. Okay, assembler output is still the same. And now in addition, we also have this output. And now actually this assembly code should be in some listing environment. So we have to modify here this code that we first print a begin listing and after that a end listing. And of course, we also have to include this LaTeX package for that. So this LaTeX header should also include use package listings. Okay, and then we should have some LaTeX code that can be translated into a PDF. Okay, now let's see. Okay, nice. And this is something that I can use in future for this lecture. Okay, so the next thing is that we also have to make sure that this assembly code is actually executable after translating it. So that means you also have to make here a few modifications. We have to print this header and footer for the code from the code generator. And this is something that we do in the test program for the compiler before and after parsing. Okay, that simply means that we will have a halt instruction in the end. The next thing is we also need a symbol table because we have this label X, which would currently be an undefined symbol if we would translate this into a machine code. And for that, we will have to make some change to the symbol table. The symbol table should print out the symbol table. So also some assembly code. Yeah. So here I want to have this function print symtab. Okay, again first check whether we have a typo. Okay, and then I can implement this function. Of course, I simply have to iterate over this list, and for each entry I have to print out an alignment and some label and some quad word. And actually I want to have segment for the data and PSS segment. So for iterating, I simply reuse this line of code, and this here can be const. And this will be the data segment. And here I check whether the value in this entry is non-zero. In this case, we have a variable which is uninitialized, which is initialized and belongs to the data segment. And if it's uninitialized, it will go to the PSS segment. So this simply means I use this function for generating some labeled unsigned integer literal. And now I simply copy this and have the variant for the PSS segment. Okay. And this should already work if there are no typos. Okay. Now let's see whether we can actually translate this into an executable. Okay. So now this is the path to my latest Ulm assembler. Bit long. Okay. And so this is the Ulm virtual machine. No error, but let's see in the debugger that this is actually some program that is doing what we stated in the program. Maybe I rearrange here the windows so that you somehow can see at least the assembly code and some registers and the memory. Okay. Now the first statement was assigning 42 to this variable x. And now you can, of course, go through this step by step and see that this is exactly what we wanted. Okay, so nice, I think. And with that, we now have a setting where we can test more expression kinds. So now we finally have reached the point where we can do some actual implementation feature enhancements. So I just need one window for making changes to the source file for expressions. And here I also want to handle this other type of expressions like subtraction, multiplication, and so on. And later also the mod operation. So I want to handle this all in one code block. That means here I have to translate this enum constants into this enum constants for the code interface. And then I also want to change the next two operands so that I also can do subtraction and division. And this is due to the fact that, for example, subtraction is subtracting the first operand from the second. And similar for division. And here I want to have this function for translating this enum constants. And currently just one for translating enum constants where all operands are registers. And this is simply done by a switch statement. And of course, this also could be generated from some description. Okay, so this here becomes gen add r, and then I can copy, paste, and modify that. Also for these other cases, of course. Okay, then we also need a default so that we do not get a warning. And in this case, we have some internal error. Actually, I could just use here an assertion. Internal errors are usually catched in the test suite. If you have a good test suite. Okay, now let's see. Okay, still a warning because here we should have a return statement even if it's never reached. So let's add it so that the compiler is not complaining here. Okay, now let's try something different. Now we have a division here instead of adding things, and also this. Here's the division, and subtraction. And then, of course, we also can do this with variables. Okay, now the next thing, I also want to support the mod operation. So that means here I also have to translate this into the operation for the code generation interface. And I also have to add here the case for mod. Okay, now let's see. Okay. We, of course, also need to change the parser. So that's the new grammar basically now implemented, that we also have here a token kind %. Now the important thing is here to not use more than 80 characters per line, and in this case I want to have the curly parenthesis, the open curly parenthesis here. And then I also have to handle this case that the operand is asterisk / or %. And in this case we have here the mod kind. Okay, and now this should work. Okay, So nice. Now you see that here the division is followed by moving register 5 to register 6. And if we have a division, then register 4 is moved to register 6. Okay, but we are not done yet. There is a kind of operation that we haven't handled so far. The unary operations, for example, unary minus. And this could be just treated as a binary expression. We could load the value 0 into one register and then handle it as a subtraction. But of course, we want to do better than that. And let me show you my simple hack for solving this kind of problem. So first of all, if we have a unary minus, or let's also consider the other example with the unary plus. Currently, these are the only unary operations that we have. Then we can do the following. If it's a unary plus, then we simply ignore this. We simply load the child node into this destination register. So this is easily handled. And in the case of a unary minus, we will simply use the fact that we know that the ULM has a 0 register. Now this is certainly not nice because you should not use knowledge of the underlying architecture in this part of the implementation. But for now, this will solve the problem, and doing better will be part of the exercise. So you now see this is working. Here we have the subtraction from register 6 from the 0 register. And of course, this also works for the unary plus now. And of course, this also works if we have a variable. And first the value of the variable gets loaded, and then again this subtraction from register 0. And of course also the unary plus works for variables. And now you of course can test more complicated expressions using the compiler. That's it for this video. There are still a few things left to do, mostly cleanup stuff. For example, loading the address of a expression, if it's an L value, into a register is an operation that we also want to use in the future in some other places. So our interface should provide a function load expression address for that purpose. And then of course also the implementation of load expression should make use of this function. Then also the current implementation of load expression uses for unary expressions some special knowledge about the underlying architecture, that we have a 0 register. This is something that actually should be hidden behind the interface for code generation. So we should provide an operation for unary minus, for example, there. So this is an exercise for you, and I'm pretty sure that you have no problem with that.